So yesterday I kind of discussed a bit about what's beyond this course, and so we see at least the definition of length constraint expanded decomposition. If you are interested, you can have a look more. There is like a web page on like that gives some tutorial on these topics. Yeah. Basically, it's kind of again like we learn about this thing and get some application to problem that is about throughput or congestion. There are a lot of things here that is more classical and get something for shortest path, and length constraint expander seem to give application to all of this. But it kind of getting more complicated too. And this is kind of some buzz, like some keywords if you want to look up later. Okay. And okay, I mentioned like a bunch of open problem that like you can have a look if you are interested on some question beyond this course. Yeah. Dynamic graph algorithm. This one is really good problem. Matching or grid reachability. I asked this. Yeah. And okay, parallel reachability. That's a really big major bottleneck in the area of graph algorithm too. And the key combinatorial object that is kind of behind all this. Behind this problem is a shortcut. Yeah, so we talk about that. Okay. Strongly polynomial time algorithms. Like both MaxFlow and shortest path. The algorithm has been stuck at running time of mn for super long time until just recently, this year or like last year. Like the bar is just broken very recently. It's very exciting, and you can wonder like if linear time is possible here. No one knows, but yeah, it's exciting. Okay, and beyond flow problem, like there's like many problems that can be captured like that go beyond flow, something that is about Matroid. And there is a course about this that you can have a look if you like to. Now I talk about one problem, which is min S cut and max arborescence packing. Okay, so it's about packing trees rooted at the node S. How many you can pack? The maximum number is just bounded by min S cut. Okay, this is kind of similar to MaxFlow min cut, but it's about trees. Okay, MaxFlow min cut is about packing ST path, and here is about packing trees rooted at S. Okay, so it's like a nice theorem, but unlike MaxFlow min cut, the state of the art still is not linear time. Okay, now another problem that it's kind of nice to at least be aware of is disjoint. Okay, so what is this? Let's say you have a directed graph. So a disjoint is a set of edges so that once you contract them, then the graph becomes strongly connected. Let's see an example. Suppose that the graphs look like this. This is not strongly connected, right? Because anyone here cannot go back. Okay. How many edges do you need to contract to make it strongly connected here? Yeah, up.
6.
6. You can do better.
Is it just? Can you just contract the big edge?
Yeah, if you just contract the big edge, then like it's gonna look like, and then kind of what, and like this, right? It's like a cycle now. So just contracting one edge here, the graph becomes strongly connected.
Does strongly connected mean that you can reach from like one node to another in both ways?
In both way, yeah. So okay, what if I don't have this edge? How many edges do you need to contract to make it strongly connected? Well, now you need to contract everything, right? So that's what is die joint. Okay, and another notion is die cut. Okay, die cut is basically a set of edges such that, like, if you have a graph and if you have some cut S, and this cut is such that every edge going out, every edge that crosses this cut only goes out. There's nothing that goes in. Okay, nothing like this. So then this cut edge here is called die cut. C here is called die cut. That corresponds to the set S. Okay. And okay. Now, how many disjoint die cuts there are in this graph? Well, one you can see easily, like this thing. This is a die cut. Okay. But there is no other die cut actually. Like that is disjoint from this guy, because if you want to get this one, then like this S is already used. Okay. So the claim is this. Like what you can see easily is that maximum disjoint die cuts, like the collection of die cuts that you can have, actually is bounded by minimum die joint. Okay. So maybe the way to see this is like this. Maybe I can say that if I have like many die cuts, many disjoint die cut, then die joint need to be at least the size of die cuts, the number of die cuts, right? Because if I don't contract any guy here, then the graph cannot be strongly connected. Okay, so mean die joint is at least number of different die cuts for sure. Okay, but it turns out that this is equal. So that's like very interesting, strange phenomenon that is true. And the proof is long time ago too. But actually the systematic proof is later by Frank. Like, so this direction is clear, but the systematic proof is by Frank, and it used something called sub-modular modular flow. Okay. Anyway, the fastest algorithm for computing minimum die join and die cuts is quite slow. Yeah, still like MN and some other factor. So Frank shows how to do it in MN square, and now Gabao improved it with. And it's totally not clear if one can improve it a bit further. Is almost linear time possible? And this is a good pathway to understand something called submodular flow, which is much more general than mean cost flow and even Matroid stuff. Okay, so but it's super concrete. So something that is so abstract here is captured by a very concrete problem that you can try to attack and understand deeper, get deeper understanding. Okay, so that's another nice concrete question. And another one is just maximum matching, but in non-bipartite graph. Okay. So you all know this problem, right? Just you have a graph, you want to find a set of edges that are disjoint from each other. Okay. Well, on bipartite graph, you know now that you can solve this thing in almost linear time, because bipartite matching, you can solve it using MaxFlow. But on general graph, the base bound is still m root n. Yeah. This is a famous result by Mikhaly and Barsirani. Anyway, if you allow approximation, Seth and Randuan, which is the first student of Seth, and now he's a professor in Tsinghua University, they get this running time, which is basically linear time when epsilon is constant. So great result. Yeah. Okay. Okay. And yeah, is almost linear time possible? We don't know, and it's a great question to think about. Okay. So this is about a bunch of concrete questions that I asked you, but this is just kind of the special case of this maybe overarching goal, which is, I think, okay, graph is so important, it's so fundamental, it's model basically anything you care, right? And I think it's really possible to get fast algorithm near linear time, even parallel, so that we can utilize many computers. Not just that, it should be simple technically. It should be maybe simple to implement shortcode. It should be simple conceptually too. That's two different things. Might not happen at the same time. It should be simple to understand. Yeah, short proof, easy proof. Okay? So this should be possible for any problem that I mentioned. Right now, we don't even know reachability. Even reachability, we don't know this. We get stuck on this thing. And maximum matching in non-bipartite graph, we don't know this too. We get stuck on many fundamental fronts. But I feel that all these things you can hope for the best for anything. Yeah. And any concrete graph problem that can be captured by submodular flow, I think it's possible. That's the hope. So can you refute this? That might be interesting for me. And if not, maybe we can try to achieve it. Yeah. 4 years ago or 5 years ago, I teach similar course like this, and I asked for let's try to prove MaxFlow algorithm in almost linear time at that time. And 2 years later, people prove it. So now now I think this is more ambitious. So maybe if you think it's interesting, we can try. Yeah. Okay. So I think this is fundamental problem, and I think it should give you a kind of deep impact in our understanding of these supernatural objects like graph. Yeah. Okay. By the way, there are some problems that I don't quite hope for linear time. Okay. But we should still think about it. I want to mention this so that at least you know about it. Okay? It's like a super simple two-state problem, and people I feel more people should think about it. So there are 3 problems. Okay, let me state it. Okay. The first problem is 3-sum. So by the way, the guy who gives the name of this is Mihai Pratascu. He's a fun guy. Unfortunately, he passed away when he's really young. He kind of changed the area of graph and a data structure in such a short time. Super smart guy. He liked to give name to problem in a funny way. Another problem that he gave a name to is a lopsided set disjointness. So that you get LSD out of this. And another problem that he defined is mean something, but the acronym is mean as. And now 3-sum. Okay. Anyway. Okay. Anyway. So he's super strong, but yeah. And one paper that he the name of the paper is How to Grow Your Balls. That's the name of the paper. Yeah. So the conference, the chair asked him to kind of change the name of the paper. So he changed that in the official version, but in the talk in the conference, he switched back to How to Grow Your Balls. Which is the paper is about distant oracle, some serious graph problem, but yeah.
Have you heard of the paper in algebraic topology that's called Hilbert-Kuhn's multiplicity and topological smoothness or something?
No.
It's a paper. It just reminded me of this. It's a paper in algebraic topology where someone is considering some notion of algebraic multiplicity and geometric topological balls. And so the title of the paper is Big Balls Implies Big Genus.
Yes. Good, yeah. So anyway, yeah. Yeah. Years ago, this kind of thing can be possible, but I don't think. Anyway, yeah. So what is this problem? This problem you get n numbers. Numbers A1 up to AN. Yeah. And you ask, is axis AI, axis IJK such that A1 plus AI plus AJ plus AK equals 0. Like the sum of the 3 things is 0. So the trivial algorithm would take n cubed time. That's trivial algorithm. Just enumerate the triples. You can just do something in n square time. Just kind of quite simple actually. Maybe you fix A1, and you kind of scan through like the rest in the kind of opposite way, so that you check if the sum is like negative a1. Okay, so like you can do this in actually n squared time. And the conjecture says that or hypothesis says that there's no like n to the 1.99 algorithm. That's a conjecture. So do we believe this? No one, like some people believe this. Someone is like in the old day, like someone tried to refute this, but they failed. And then like, so people now start to just say that, okay, let's say that it's just hard. But there is value on this, because once you assume that it's hard, then it implies that if you assume that it's hard, then it's explained that other problems are hard too. Like you can say like there are some other problems that if you can solve problem A faster than n squared, then you can solve 3-sum faster too. And this you can do it. Actually now like there is this area of called fine-grained complexity. Fine-grained complexity theory, right? Which is about showing this kind of reduction. Like assuming 3-sum is hard, what else you can say that is hard too. So it's good, it's explain things. Like it say that, okay, 3-sum is a barrier that you need to, that if you cannot solve 3-sum, then you cannot do anything else. But I feel that like lately, people just assume it as a truth. So like that is not cool to me, at least. Yeah, I think like we should come to here and like find some angle to attack the core problem, right? So that's like what I want to motivate. Yeah, the core problem. Okay, it's hard, but we should find some angle to attack it. There is a similar problem, which is APSP, all pair shortest path. Okay, what's this problem? You have a graph and you want to compute the distance between every pairs. Okay, now this turns out to be like the fastest algorithm is n cube, and the conjecture is that no, like n to the, like you cannot improve n cube. Okay. Same scenario happen. Like if you assume this, it implies many other things that is hard to. But is it correct that you cannot really do it? Yeah, like we should try to attack it. So interestingly, this problem is equivalent to another problem, which is about, it's called negative triangle. Like imagine that you have a graph where some edge is like a negative, some edge is positive. And you ask, is there a triangle such that the sum is negative? If you can, like this problem is clear that you can solve in n cube time, just enumerate the triple. If you can improve the running time of this from n cube to n to the 2.99, you can solve this thing too. So can you solve this faster than n cube? That's the question. Yeah. So, okay. Like the last question is this. It's called orthogonal vector, which is defined like this. Let's say you have a 0, 1 matrix. here is of size n, here is of size, let's say log square n. This is matrix, one matrix A, and you have another matrix, 0, 1 matrix. This is n, this is log square again. This is B. Yeah. And you ask, you want to multiply, like you ask when you multiply this vector together, is there like a 0 here? Exists 0 here. So that's a problem. And is the problem clear? You have 0, 1 matrix, you multiply, like you multiply them, but you don't want to multiply and write down everything. You just ask if there is a 0 inside this matrix. Like the algorithm is clear that you can do it in n squared time polylog just by multiplying this matrix trivially. Like each entry, you can multiply them, and then in time n log square, there are like n square many entries here, so that you can do this. And the conjecture is that no fast algorithm. Yeah. So that's the question, and same story again. Like, so these are like the key problems, 3 big problems. Like they call it big 3 in this area. That once you assume that they are hard, it explains like by now like not maybe 50, 60 other problems, something like that, why they are hard. But not too many people try to attack it. Maybe like people like Ryan Williams try to attack that, but maybe more algorithm people should try to do it. Like Ryan Williams is like, yeah, he works on complexity. Yeah. Okay, so that's the thing. So I think like, yeah, people should try more to refute it. Like so like I think trying to look for the deepest question that you think is fundamental, and try to get approachable angle, yeah, and attack that. That should be like a nice research, nice goal to do, yeah. Right. Okay, so yeah, before we stop now, like yeah, is there anything you wanna ask? Yeah, now is the time. Yeah.
I mean, do you have a guess for which of these 3 problems is the least likely to, which of them you think is the least likely to be true?
I would start with APSP. Yeah. Why? I don't know actually. Yeah.
When you say like people assume these problems are hard, I guess I'm wondering like which way you mean, like hard as in like it's impossible to get better than n squared, or hard as in it's hard to make progress, research progress.
Good.
Yeah. Which one are people thinking?
Right now, I think it's both. Like, so, like the conjecture is there so that the point of this conjecture is there so that like it identifies the important barrier, but the name, the fact that we call it conjecture, maybe makes people feel that maybe we shouldn't attack it. It should be true.
Okay.
But there's no quite like a reason to believe it should be true. Yeah.
What's like the lower bound for those problems? Like, is there any lower bound?
No.
No. Like
All of this can be linear time.
oh really?
Yeah.
That would be kind of crazy.
Yeah.
Is there? Do you have like an example of a problem where like people were not sure if it's linear time, but then someone come up with like unconditional lower bound?
There is no unconditional lower bound right now for any problem. Yeah. Like, so,
For any of these problems.
like, what I mean is this. So, I mean, there are some unconditional lower bound. Like for some problem, like of size n, like people know that you might need like a 3n operation, something like that. Like, so more than n, 3n, something like that. That is possible. But like there's no conditional lower bound like more than linear, not like, no, yeah. So like our ability to prove lower bound right now is actually really low. Yeah. Yeah. So that's why like these conjectures are really useful in that sense, because if you assume it, it at least gives explanation why other problems are hard. Yeah. 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 More questions?
Kind of returning to some of the max flow discussions, do you think that the barrier in like near linear time max flow is do you think that's more of like an analysis barrier, or are there like significant algorithmic improvements that need to be made too?
Very good. I think we need some new algorithms. Reason is that like at least the push level algorithm that we discussed in class, we use the push level algorithm that is, if you remember, is relabel aggressive. You try to relabel as much as you can. But for that approach, even if the graph is a path, you spend n squared there. Okay. So the algorithm need to change, that's for sure. But okay, the path, maybe like there is some other ad hoc way to just attack a path. But yeah, so like it seems possible, but maybe some change in algorithm is needed. Yeah. 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 Any question about anything about the contents in class, about exam? That's okay too. Yeah.
It's also a question about max flow. So like, what's the best algorithm like in practice?
Yeah, so this is what I kind of heard from other people. I don't really know firsthand, but like people just say that just use push the level, standard thing,
Oh,
without any linked tree.
oh,
Just do that. It's fast already.
it's a mn squared.
Yeah, the mn square.
Oh, that's the fastest.
Yeah, that's like, yeah. So there are like some, so you know, like Andrew Goldberg, the one who came up with push the level, he is the one who also like solve MaxFlow in real life as well. Like he's at some company, Microsoft or something. I don't remember, but like yeah, he has some paper which just say okay, do push the level, don't use link cut tree, but some variant of that. Yeah, maybe it's choose where to relabel, where to push a bit more carefully, and it's fast.
Is there an obvious reason why like top trees are like slow in practice?
Yeah, so yeah, top tree, link cut trees, or something similar. I think it's slow because like the constant that is hidden in the log in the big O notation is kind of maybe like big, that's maybe the reason why. I'm not super sure. Yeah. There are several papers that experiment on this. So,
Yeah.
like, because sometimes, like, this is about also like locality, like about cache. Yeah. Like some algorithm that kind of exploit cache will be much faster than algorithm that don't exploit that. And at least in this class so far, we don't think about cache at all. Yeah.
So okay, so it's also like a hardware issue that's sort of like
Yeah. Yeah. Yeah.
It's kind of follow up. So like, do you think the fast algorithm that we learn can eventually be like faster in practice than like?
Can it be fast in practice? Good. I think it is possible, but we need to work on it. So, for example, a lot of fast algorithm in basically the whole thing here. When it's fast, we base ourselves on cut machine game. The cut machine game right now has running time of this much at least. Log to the fourth and the constant here, not super sure. Okay. It's not like, at least it's not too complicated to at least describe. So I don't think the constant here is too big, constant inside. But I think log to the fourth is still quite big. Yeah.
So I think the log to the fourth can be improved.
It should be possible, yeah. Something like log square may be possible. Yeah. Yeah. Yeah.
To get log squared there, you would need probably like both an improvement in terms of the rounds, but also the running time of the algorithm then, or?
Yeah, maybe like if the number of round is log n, in each round you spend like m log n, then that's log square. Yeah, I think that's maybe like what I hope for. Yeah. Yeah. Okay, more questions? All right. Okay, then yeah. So I guess we're gonna meet online, yeah, to talk about exam and project and scribe if needed. And yeah, this is a course that I really cannot spend so much time to prepare the lecture. So I really hope that at least you get a feel of what is at least in the frontier of graph algorithm, at least in one particular area. Yeah. So even if you don't use it later, at least you feel what it is to be at the frontier. And if you use it, I would be glad and happy to talk and discuss more if you are interested. Yeah. So yeah, thanks for this course. Yeah.